Thanks a lot for having me here. It's a pleasure to talk at Open Source Day. And this is what I'm going to talk about. It's not a specific topic, it's a bunch of topics that are related to my career as a musician, developer, and astrophysicist. So let me just start without further ado with the talk. So let me just give you a brief outline of what I'm going to talk, what this is going to be all about. So I just want to tell you how I got into programming and software development. So I started as doing cosmological simulations, and how I switched to the world, so the observations of the world with machine learning and satellite data. And then I'll talk a little bit about NanoRow. I don't know if anyone of you knows about my band, but this is also something I'm pretty proud of that I have achieved. And so I'm going to talk about a couple of songs that are related to astrophysics and programming. So it's going to be just a mixture of topics, and I hope you'll bear with me if it's going to be quick, but I hope at least it's going to be interesting. So let me start with the universe. So I started coding because I did a PhD in astrophysics, and it turns out that if you want to understand the universe, no one nowadays really, basically no one does things like with paper and pencil. They really need to know how to use computers and do calculation on a large scale. So if you want to understand how the universe from the initial stages of the Big Bang moved on and so this is, you see on the x-axis is time, and these are just slices that you find. On the y-axis, they are two-dimensional slices of the universe, so you see how from this point, from the Big Bang, things evolve and turn into galaxies, planets, and everything that are around us. It turns out that if you want to do this kind of, if you want to understand how these things are related, how the whole universe is moving from from point A to point B, you need to rely on computers and cosmological simulations. So these are all the scales that are involved. We start from the Earth, that lives within the solar system, lives within the solar interstellar neighborhood, within the Milky Way galaxy. So we are in this part here on a spiral arm of the Milky Way, which is part of a local galactic group, which is part of a supercluster of galaxies. So there's many tens of galaxies together, if not more, there's hundreds actually, that form the Virgo superclusters. This is part of another system that is part of the observable universe. So we want to understand basically how all these things are related. There's so many scales involved. And when you do this kind of thing, when you want to understand these kind of things, what you're doing is cosmological simulation in which you put a bunch of particles in a box and you trace, you write code that traces the gravitational evolution of these particles. How do they interact with each other in different stages? So you have these boxes full of particles. Let's say every particle is like a planet, a star, sort of, and they evolve, and you see that from very back in time, you move through different phases until you go to what you see today, which is this kind of filamentary structure in the universe where you have very high density regions. There are clusters of galaxies, and they are connected by these filaments. And there are large voids where almost nothing is there. And this is just to show you what this thing looks like. It's a very... The music is not so nice, but the video is probably just to show you. As you see, you start from this very homogeneous distribution of particles, and eventually they collapse. And this is how you form stars. You form galaxy stars and clusters of galaxies. And so the bottom line is, to do all this, you need to write software. So most of the times this software is open source. There's many universities cooperate together. And part of my job was to write code for that. So let me just skip this one. And I have two open source projects that have pretty nice names. I hope you don't find them, the second one, offensive. But this got viral on GitHub, and it's a legitimate scientific project. So first of all, it's merger trees on C++. This is merger tree. Let me start with the first one and tell you, this is the first software. It's basically a software that computes the ages with which galaxies in a cosmological simulation forms, which is, for me, it's comparable to the time that the metro C line in Rome formed, because it's taking basically billions of years, just like the formation of galaxies. That's where the inspiration came from. And then we have these Python routines for cosmology and data I/O, also known as Parcod.io. which is part, by the way, this is part of the Arctic Code Vault. So it was elected by GitHub. It's going to be there forever and ever until the end of time, and I'm pretty proud of this thing. There was a flame on GitHub. I don't know. Sometimes I get stopped by programmers at concerts and stuff that they ask me, "Oh, you're a hero. You did this thing," and because there was a fight. So I hope I'm not offending anyone, as I did on GitHub. No, actually, that's a separate. So I wrote a paper about God, but. Let's not delve into that. I got a paper, it's called The Foundations of Gauge Theology, that explain how particle physics explains God. Not really, but it's fun. But this one is for data analysis. So I'm taking this kind of software. It was made, it's open source. It's open source project. I use it on a bunch of papers to analyze cosmological simulation and produce nice scientific results that got on many papers, like this one. These are just to show you the repos of PyRCoDio and Metro C++. And this is how I started to transition towards machine learning. So at some point, I basically used machine learning tools to analyze cosmological simulations. PyRCoDio was part of my tools box in this process. But the idea is that I started studying cosmological simulation, so extracting information. I was training machine learning models on synthetic data from simulation, and then applying it to observation to get real results. So the idea is that with machine learning, so with synthetic data, of course, you have all the variables. They're under control. You know everything about, if you have a galaxy, see a simulated galaxy, you know everything about that galaxy because, of course, you're putting that in your computer. And so the idea is that you want to extract some feature, the ones that you normally observe. Of course, you cannot observe everything about other galaxies in the universe. And so you just take the observable features and try to train machine learning model that allow you to extract unobservable features from the observable ones. In our case, it was the mass of the local group of galaxies, which is the Milky Way and Andromeda. So it turns out these masses are not very well known, despite the fact that we are very close. So we cannot measure them directly, but we can measure, for example, the number of stars. We can measure the velocity of stars in the galaxies. And so we can connect those kind of features with machine learning to the mass of the galaxy. So this brought me to a career switch, which is, so what happens if you point the direction of the telescope to the Earth? Instead of to the stars. So what if you want to study the Earth instead of studying the stars? And this is what I'm doing right now. I'm doing machine learning for satellite observations of the Earth. And this is a pretty cool project, first of all, because most of the data, there's lots of data that are open source from ESA and NASA. There's the Sentinel missions, for example, and the Landsat missions that provide free and open data of the Earth. So you have these satellites that orbit around the Earth, and they take pictures of the Earth at constant frequencies. So every 5 days, for example, is the frequency of Sentinel-2. And the nice thing about these pictures is that you don't have just the RGB image, but you get also information about other frequencies, not visible by the human eye, but you can detect them with the proper instruments that are put on board of these satellites. And so you have information about ultraviolet, for example, near infrared, shortwave infrared, which means that you can monitor and gather information about a bunch of very interesting phenomena on Earth. And so let me move forward with this. This is, for example, if you take a picture of Venice, this is how it looks in RGB, but this is the infrared picture. So if you want to have information about any place on Earth on non-observable frequencies, you have a good chance to use these missions, and you can do a lot of cool stuff with this. And let me just show you one application. As I said, this is open access. So there's Copernicus portal, but there's also Google Earth Engine. There's a bunch of portals that you can access freely, and you can get images dating back from the 80s of the Earth. So you can trace and monitor the surface of the Earth at different stages. And the thing is that one important variable, and just to put one practical example on how you can use this data in practice, is that the chlorophyll is very sensitive to the near infrared. So if you take pictures in the near infrared, you can build this NDVI is normalized difference of vegetation index, which is constructed in this way. So you have the near infrared value of the picture, you get the red value of the picture, and this is related to the health of the plant. So it's related to the, you see it's linearly related to the chlorophyll. This is the chlorophyll and this is the NDVI value. And so from space you can basically monitor the status of, the state of health of vegetation, which is a pretty nice thing. For example, if you want to know if you can make this kind of classification, you can also do this kind of classification with machine learning and segmentation models, which I'm not delving into, I'm just quoting it here, but I just want to tell you that the main goal of this thing is, of course, to be able to monitor the changes, for example, in land soil application, or simply to find out whether some areas are in danger for, in the sense that the chlorophyll value is very low and it's getting degraded, for example. And one, the last application that I'm going to mention, so this is, I apologize for making this a serious part of my talk, but this is going to be the last part. And I'm going to mention one project that we are working on is this daily fire hazard index, which is this weird number here that you get, but the main idea of this daily fire hazard index is that you can monitor from space the state of health of the vegetation. And so once you know whether the vegetation is dry or not, you also, and you combine that with meteorological data coming from, for example, there's lots of open source meteor stations that provide open access data. You can build, you can monitor basically the risk, the likelihood of fire ignition, of wildfire ignition due to the presence of dry vegetation and adverse meteorological conditions such as very high temperatures or winds and stuff. So this is one of the kind of the maps that you can produce. For example, for Sardinia, you can see these are the very high risk areas that are, and you can make this kind of plots on basically near real time. And so it's useful because you don't need to monitor every point in every forest on Earth, but you can use these pictures from space to analyze them and have almost near real-time update on the state of health and so the risk of fire. So let me get to the interesting part of the talk. What about Uranus Hello World.java? So I don't know how many people know Nanoroar of Steel. I just want to spend a few words about my band because it's basically the most important thing I achieved in my life. So we are active since 20 years. Actually more, we celebrated 20 years 1.5 years ago in Milan, in Alcatraz. This is me with you can recognize me because of the orange wig. We just came back. I came back 5 days ago from this nice European tour. We did this Dynasty from Sweden. So it was very, very cool tour. Lots of concerts, a lot of fun. These are some pictures taken from this last live, from this last tour that we had. So this is just to show off and show you that we are actually doing stuff with this band. It's not like a garage band that plays in local venues. So we had the idea to do with Nanoroar of Steel to put all this science and programming into songs. And the first thing we did was this Uranus song. It's double meaning. I'm not explaining too much, but I think if you're fluent enough with English, you might understand what it's all about. We shot it at an observatory in Campo Imperatore, which now I can say at the time then the director of the observatory didn't really understand the joke. He understood it when it was too late, when he already shot the video. So at that point he complained for being too explicit, but it is what it is. So we went to this observatory and shot the video with a bunch of dancers, and I want to show you just a little video.
I like it big, I like it cold, I like it blue, I like it bold, I like it with the 2% of methane. I want it icy, I want it large, want it spicy with electric charge, fluid outside, a rocket side.
Well, so this was a piece of the song, but the whole song, as you can see, it's about science and astronomy. Astronomy with 2 S, so it's astronomy. So this is one of the things we did, but in recent times, like in December, we released this song which almost went viral on YouTube and on Instagram. We got a few million views scattered along the different social medias, and we made a repository of the song. It's helloworld.java, so it's the dumbest piece of code you can think of, but we made an epic song out of it. And actually, this is a screenshot from a few weeks ago, but it had like 1.7K stars. There's lots of forks. We got a lot of pull requests, and you can check it out. We made the nanowar of steel on GitHub. We made our project repository, and this is one of those. Then we're gonna add stuff because I think we are the first band that now we are being endorsed by JetBrains with their IDE. We seriously get endorsed by that. We are making merchandise. We have projects about songs and other. So it's gonna be. We already released something. I'll show you what we did. But for those who don't know, this is the video. I'll just show a part of it.
Still not hello world. Public class, hello world. Main launcher class. Public hello world. Main launcher class. Round brackets and food. Zero round bracket is not full equals food. Semicolon close bracket. Round integer. Full equals zero. Public voids are refrain. Round brackets. Open brackets. When time equals zero. Less than full plus plus. System out of return. Hello world. Semicolon. Int people equals zero. One people less than full. System out of return. Hello world. People plus plus. Double close brackets.
It's available on YouTube, but now it's. Thank you. It's probably too long to show the whole video. I don't know. We already started late, but you can watch it, and it goes on. The funny thing, the important thing about this video, it ends with a no pointer exception. Very sadly, yeah. The song gets disrupted by a no pointer exception. And then we got contacted by JetBrains, and they say, okay, well, you can use the IntelliJ IDEA to fix this bug. The bug was actually, we set this Boolean metal variable to false, and so now it should be set to true. That's the way, then, if it's set to true, then the code runs, because we play true metal. That's a joke. But I will show you how we fix this. Then we release the patch of the song, and we released, and this is actually the actual video patch. The exception part, so.
System out of print element. Hello world.
Thank you. Thanks to JetBrains, we made the code work. Otherwise, it would have been impossible to change the value of that variable from false to true. And anyway, so that's. I think that's it. Close on these funny notes. And thanks a lot for listening and watching my talk. Thank you.
What a journey from geospatial data to a song based on Java. Wow, that was amazing. Huge fan, personally. I think there are a lot of fun right here of the world. And if anyone has got any question, don't be shy. Oh, okay.
Thank you. First of all, congratulations for everything, for your work in every area, in every different area. That was genius. I loved it so much. I was fascinating about the analysis of the vegetation, and I have a quite curious question. How is the analysis built? You said that you can check the health of plants, but how does it do that? I mean, is the whole area, is per plant? How much is specific, let's say?
So, I didn't say that. It's a good question, because it depends on the resolution of the satellite mission that you're using. So there's different satellite missions, and the best resolution that is freely available now, it's Sentinel, and it takes pixels that are 10 meters of size, which means there's a bunch of trees. So I don't know how many now. There's a number of trees within a single pixel. And this pixel, you can get the value, of course, the infrared value and the red value. And if you do this combination, algebraic combination of the two bands, then you can get, it's a proxy. It tells you basically how much chlorophyll you have in that area. And so the chlorophyll, of course, is related to the status of health of the vegetation. And the thing is that, of course, if you have a historical series, you can get images from the 80s in some missions, but usually for Sentinel-2, it's to 2016. But if you're happy with data ranging from 2016 onwards, you can get, if it's changing, like if it's sloping downwards, if it's going upwards, if it's greening, if it's not greening, you can get this kind of trends. And again, Sentinel is 10 meters. There's missions that go to 20 centimeters, half a meter. There's also models that we are trying to use that do super resolution, so you can get a 10-meter image, but then you can improve the resolution. It's sort of, you increase it with some kind of, there's the UNets.
So if you want, you could check every plant.
Yes, I mean, that's actually, we're working on a project where we're doing sort of that. So we're mixing data from private missions, which usually are on a per pay basis. There's Airbus missions, for example, the Pleiades. I think they go to half a meter resolution, so you can really see like the plant. But then you can use the free data plus these resolution enhancing models that are pretty good. They are surprisingly good. And then you can really check the state for single trees, yes.
Beautiful. Yeah. Good luck with your job.
So, someone want to earn some points with another question? Gonna be there soon.
Yeah, thank you. I was wondering if you are going to release any other songs, maybe in helloworld.js or PHP for those who doesn't understand Java.
So we wanted to do a Python cover of the song, but then we would like to do something different. So now we are thinking about making maybe a full album on a repository. So you make the Docker file, you can, like all these kind of aspects. We are thinking about different, we have many ideas in mind with JetBrains. We are actually really working with JetBrains. We are making songs about, this is like a spoiler, but we are working on a song about Kotlin. So, and the next step, I want to do. I mean, I'm a C++, Python guy, so I have some ideas for C++ and Python. The problem is that with the band we have so many things going on at the same time, and it's. But we'll add something. We'll add everything to this repository that we have. So.
Yeah, cool, wonderful.
Yeah, thank you.
Just one thing. Why don't you do a cover of Do Hast and Do Rust?
You want the honest answer?
Any other question? Okay, so round of applause. Oh, sorry.
Sorry? We don't know Rust.
Yet. Round of applause.
Thank you.